Today we are going to look at Lagrange multipliers and especially how the use of Lagrange multipliers differs from the use of Cauchy-Tucker conditions. Now, in the sketches here you can see the two areas where they differ. If I have some set of constraints, such as for instance we had in the video on Cauchy-Tucker conditions, with the Cauchy-Tucker conditions you are always considering some kind of inequality constraints, and in general this means that you have constraints indicated by the lines and an inequality, which means you are looking at the area inside these lines as well. Now this figure could look vastly different, but that's the general idea. When you're using Lagrange multipliers, you are only looking at the edges of the constraints, so you do not consider solutions on the inside of this figure at all. Now, for instance, if you look at this sketch down here, we have some kind of concave function and some kind of constraints indicated here in blue in the xy plane. Z indicates the function value, and that corresponds to some part of the figure indicated here in green. What we're essentially doing then with the Lagrange multipliers is to look at the possible maximum of the function over all of these lines indicated here. When we use the Cauchy-Tucker conditions, we'll actually be looking at the inside of this figure as well. Now, how do we actually do the Lagrange multiplier method? This is a question, I think, from question 10 of the mock exam that I posted. Here we have a function of x and y equal to 2x squared plus 3y squared plus x minus 9y plus 16, subject to two linear conditions. In the mock exam we actually only use one condition, and we'll see later why this makes it actually a more interesting problem. Now, if you're used to working with polynomials, you should suspect immediately that this is a convex function, and we are looking for the minimum of this function over these constraints. So the first thing we do is we write these things in the right form. So if we create a function gxy is equal to x plus y is equal to 5, so g of 1 is equal to x plus y is equal to 5, which is our b1, and g2 is the second constraint, that is minus x plus 2y is equal to minus 1, and that is equal to b2 in the notation that we use. Then we construct the Lagrangian function, which is a function of x, y, and two Lagrange multipliers because we have two constraints. So, as usual, this is just the ordinary function value, and then we add the constraints lambda 1 times b1 minus g1, and you add the second constraint lambda 2 times b2 minus g2, so it's minus x minus 2y. Now, to get the solution to this problem, we just need to get the partial derivatives of this function and set them equal to 0. So first one, dl dx is easy, it's just 4x plus 1, and there's an x term in the lambda 1 term with a minus in front, so it'll be minus lambda 1 and plus lambda 2. And the partial derivative with respect to y is 6y minus 9 minus lambda 1 minus 2 lambda 2. And unlike the Kuhn-Tucker conditions, we also take the partial derivatives to the Lagrange multipliers. Now this actually is no different than the Kuhn-Tucker conditions, and we'll see why in a moment. Now the only term in which lambda 1 appears is up there, and so the derivative is just b1 minus g1, and the derivative to lambda 2 is just minus 1 plus x minus 2y. And of course we set all of these equal to 0. Now this looks very similar to the Kuhn-Tucker conditions, except we don't have lambda terms in these last two equations. Now this is very close to the case where we're already assuming that if this were the Kuhn-Tucker equations, this would be very close to assuming that our lambda 1 and lambda 2 multipliers are not equal to 0, because in that case we would have to have that the functions are equal to 0. And as we discussed in the previous video on Lagrange multipliers, on Kuhn-Tucker conditions, when those lambdas are not equal to 0, then we are actually working on the edge of the given region. So there's a great correspondence between the Kuhn-Tucker conditions and the Lagrange multipliers. Now in this case, solving for x and y is actually very easy. If we call this equation 1, we call this equation 2, we actually just need to add the two. If you add 5 and minus 1, you get 4. If you add x and minus x, you get 0. If you add minus y and minus 2y, you get minus 3y. And so you get a very easy answer for y. And of course, we then have from, say, equation 1, 5 minus x minus y is equal to 0, so 5 minus x is equal to y, so x is equal to 5 minus 4 over 3, which is 3 2/3. Now this seemed very, very easy to solve, easier than most problems of this kind, and that's because if we actually consider what we were doing here, we were looking at two constraints which are linear, and as usual, linear constraints, two linear constraints only have one intersection. Therefore there is only one point at which these two functions intersect, and therefore only one point at which the constraints will be satisfied, and that will clearly be the minimum point on which both constraints are satisfied. So in this case, actually adding more constraints of this type makes the problem much easier. So let's instead consider this problem the way it was already given. I'm just going to write it down here again. Our function to minimize is 2x squared plus 3y squared plus x minus 9y plus 16, subject to x plus y is equal to 5. I have only one condition, only one Lagrange multiplier, so the Lagrangian becomes easier, but paradoxically actually harder to solve. Plus lambda 5 minus x minus y. So once again we look at the partial derivatives, which will actually just be the same as the previous ones, with all lambda 2 terms removed. And the derivative to lambda is just 5 minus x minus y, and all of these things are set equal to 0. Now solving this isn't too hard. We've got from the first equation up there, put 1, 2, and 3. Now from 1 and 2, we can take the lambda to the other side, and we'll see lambda is equal to 4x plus 1, and lambda is equal to 6y minus 9. Since lambda is equal to lambda, we have 4x plus 1, let's take there, equal to 6y minus 9. So we can easily solve for x in terms of y, and what does this give us? For x plus 10 is equal to 6y, so we can divide by 2, make it easier, so 2x plus 5 is equal to 3y. But we also have the other equation to work with. So from 3, we know that y is equal to 5 minus x. So 2x plus 5 is equal to 3 times 5 minus x, which is 15 minus 3x, and therefore 5x is equal to 10. So easy enough, x is equal to 2, and since y is 5 minus x, y is equal to 3, and lambda from the equations above is equal to 1 plus 4x, or 6y minus 9. So lambda is equal to 9. Nice tip, if you want to make sure that your solution is correct, or at least an indication that it is correct, if you look at these equations above, you have lambda is equal to 4x plus 1 and lambda is equal to 6y minus 9. So if I evaluate lambda according to x, I get 9. If I evaluate lambda according to the y expression, I get 6 times 3 is 18 minus 9 is equal to 9. So if these two expressions give you different values of lambda, you'll know you've gone wrong somewhere. Now, the question is this enough to answer the question and to get you full marks for your question? No, not quite. Just as with the Kuhn-Tucker conditions, we had to verify that this is indeed a solution. And what will guarantee that? Well, in the book you'll see with the sufficiency conditions for the Lagrange multipliers, you need to know that f is convex, because this is a minimization. Now, how do we find out if the function is convex? Well, easy enough. Just as with the Kuhn-Tucker conditions, we take the second derivatives and construct the Hessian. Second derivatives are easy. The first derivative to x is 4x plus 1, so the second derivative to x, d squared f dx squared, is equal to 4. df dy dx is equal to 0. So if you take the derivative of df dx to dy, you get 0, and that will also be the same. There needs to be a 2 there on top. Also the same if you first take the derivative to y and then the derivative to x. Remember, as we said, for these nice differential continuous functions, the second derivative to x then y is the same as the second derivative to y and then x. Now df dy is equal to 6y minus 9. So d squared f dy squared is equal to 6. So now we can form the Hessian matrix, which is very easily 4, 0, 0, 6. Now what are our first principal minors? They are just the diagonal elements 4 and 6, and they are both greater than 0. Now the second principal minor is the determinant of this matrix, which is 24, which is greater than 0. So therefore we can conclude f is a convex function, and therefore the solution that we found is 2, 3 well, this is actually slightly wrong. I shouldn't write it like this. Let me scratch that out. 2, 3 is not a minimum. I should say that the minimum is found at 2, 3. Now, is this enough? Well, there's actually still one very, very important step. The question is to minimize the function, not just to find out where the minimum is. So we actually have to include in our answer the minimum itself. So we need to evaluate the function at 2, 3. So here we have, let's see, that's 8 plus 27 plus 2 minus 27 plus 16. As 27's cancel out, so we have 10 plus 16, and we have a minimum value of 26. And that answers the question in full. Now, one thing to mention still is that we can use KKT conditions with equality constraints, and in fact this is very important to be able to do. In the same way, you can actually answer these Lagrange multiplier questions with KKT conditions if you use this method. So we had an equality constraint x plus y is equal to 5. Now that's the same thing as saying that x plus y is less than or equal to 5 and x plus y greater than or equal to 5. Because if something has to be less than or equal to 5 and greater than or equal to 5, it can only be 5 itself. Now we have a slight problem here because we require that all our constraints be of the form less than or equal to. So if we take x and y to the other side, we get them in the right form. So our one single equality constraint becomes 2 inequality constraints. X plus y less than or equal to 5, or minus x minus y less than or equal to 5. So there's a good exercise for you in the use of KKT conditions. Solve the above minimization problem by using KKT conditions instead of Lagrange multipliers. Now, there's one thing that I have to still mention, which is a difference between these two, and it's very important to remember when using your KKT conditions. When we use Lagrange multipliers, we don't place a restriction on the value of that multiplier. But in KKT conditions, it is always important to have your multipliers larger than or equal to 0.